In part C, we want to look at conditional expectations, and we want to find out what is the mean of n conditioned on the fact that n is greater than 0. We can do this in two different ways. In the case where you have the conditional distribution given, then you can actually figure this out using the conditional distribution. Let me explain what I mean by that. In part B of the exercise, we figured out that the probability that n is equal to 1, given n greater than 0, well, this probability is equal to, what was it equal to? It was equal to 3/4. So, since given that n is greater than 0, n is either 1 or 2, then n being 2 is just a complementary event, which has probability 1/4. This is the conditional distribution of n given n greater than 0. And since we already have the conditional distribution, then we can just say, well, the mean of n given that n greater than 0, well, we can just kind of look at this whole thing as one stochastic variable and say this is equal to the classical definition of the expected value, where I let n go from, well, let's see, here n has to be greater than 0, so I let n go from 0 to infinity, and I have n multiplied by the probability that n is equal to small n, given that n greater than 0. So I just use the conditional distribution here, and then I have, well, for n equal to 1, I have to multiply with the probability 3/4. For n equal to 2, I have to multiply with 1/4. And then n can't have any other values, so this is just equal to 5/4. So that's one way of doing it. It's by basing the expected value, the conditional expected value on the conditional distribution. Another way we can do it is by looking at the definition of conditional expectation that I give you guys here. And it's also the one that we get at the bottom of page 18 in the lecture notes, except that in the lecture notes they give you the continuous version, and here we use it in the discrete case, but it applies nonetheless. So if we use, using the formula from page 18 at the bottom, we get that the mean of n, given that n is greater than 0, is equal to 1 over the probability that n is greater than 0, multiplied by the expected value of n multiplied by the indicator of n being greater than 0 of n. Now, what do we mean by this? Well, first of all, n is greater than 0 with probability 0.2, so we can just add that down there to begin with. And second of all, we can figure out the mean of this by just thinking of this thing inside here as a function of n. Actually, I have written up what the exact definition of this is in terms of a sum. So it's equal to the sum of, so we let n go from 1 to infinity, and it goes from 1 because the first term for n equals 0 cancels out anyways. So it's the sum of n multiplied by the indicator of n being greater than 0, multiplied by the probability that our variable attains the value n. And this is equal to, well, for n equal to 1, we have that this indicator evaluates to 1. So that's good. And then we have the probability that n equals 1. And also for n equals to 2, this indicator also evaluates to 1 since 2 is indeed greater than 0. And then we just multiply with the probability that n is equal to 2. And this is equal to 0.25 divided by 0.2, which is equal to 1/4 over 1/5, which is 5/4. So we arrive at the same result by the two different approaches. Now let's also use the second approach to figure out what the mean of n given n greater than 1 is. So now we want to find what is the mean of n given that n is greater than 1. Strictly intuitively, we know that if n is greater than 1, it can't be anything else than 2, right? So intuitively, we actually expect this to give the answer 2. Our expected value for n, given that n is greater than 1, well, it must be 2 because it can't be anything else. It can't be 1, it can't be 0. So that's our intuitive answer. But what is our mathematical answer then? Well, this thing here is equal to the mean of n multiplied by the indicator of n being greater than 1 of n divided by the probability of n being greater than 1. So this is just the same as dividing by the probability that n is equal to 2, because if n is greater than 1, then n must be equal to 2, and if n is equal to 2, it is also greater than 1. So this is just 1 divided by 0.05. And then we have the mean value here. So what we have is the sum for n going from 1 to infinity of n multiplied by the indicator of n greater than 1, and then multiplied by the probability that n attains this value n. Now let's try to write this out. So for n equal to 1, we get that this indicator function evaluates to 0 because 1 is not strictly greater than 1. For n equal to 2, the indicator function evaluates to 1 because 2 is indeed greater than 1. And then we multiply with the probability that n is equal to 2. So we see here that the first term cancels because of our indicator function. And then what we have left is, well, the probability that n is equal to 2, which is 0.05, divided by the probability that n is equal to 2, and then multiplied by 2. And this is just equal to 2 as expected. So that was your first exercise of conditional expectations done 2 ways. Try to look at this video again if you found that confusing. Especially the indicator notation may take a little bit of getting used to, but it's okay. Just take a look at this. Slow and easy does the trick.